Volcano formation process. Volcanoes are formed through a combination of geological processes. They are typically associated with tectonic plate boundaries, where the Earth's crust is divided into several large plates that float and move on the semi-fluid layer below. There are three main types of volcanoes: subduction zone volcanoes, rift zone volcanoes, and hotspot volcanoes. Subduction zone volcanoes. These volcanoes form at convergent plate boundaries, where one tectonic plate is forced beneath another in a process known as subduction. As the subducting plate sinks into the mantle, it starts to melt due to the high temperature and pressure. The molten rock, called magma, is less dense than the surrounding rock and begins to rise. Eventually, it reaches the surface, resulting in volcanic activity. Examples of subduction zone volcanoes include the Ring of Fire around the Pacific Ocean, where the Pacific plate is subducting beneath other plates. Rift zone volcanoes. These volcanoes form along divergent plate boundaries, where tectonic plates are moving apart. As the plates separate, magma from the mantle can rise to fill the gap, forming a volcanic rift zone. The magma reaches the surface, creating volcanic eruptions and the formation of new crust. The East African Rift System, including Mount Kilimanjaro and Mount Nyiragongo, is an example of rift zone volcanism. Hotspot volcanoes. Hotspot volcanoes are not directly associated with plate boundaries. Instead, they occur due to localized areas of intense heat in the mantle, known as hotspots. These hotspots remain relatively stationary while the tectonic plates move over them. The rising magma forms volcanoes at the surface. Famous examples of hotspot volcanoes include the Hawaiian Islands, with Mauna Loa and Kilauea being prominent examples. Regardless of the type of volcano, the magma that reaches the surface is often rich in dissolved gases, such as water vapor, carbon dioxide, and sulfur dioxide. These gases can cause explosive eruptions when the pressure is released, leading to the ejection of volcanic ash, gases, and lava. It's important to note that while these are the primary mechanisms for volcano formation, there can be variations and unique geological circumstances that give rise to different types of volcanoes. The study of volcanoes and their formation is an ongoing field of research, and our understanding continues to evolve. Plate tectonics plays a significant role in the formation of volcanoes. Volcanic activity is closely associated with plate boundaries, where the Earth's lithosphere, the rigid outer layer comprising the crust and upper mantle, is divided into several large plates that interact with one another. There are three main types of plate boundaries: convergent boundaries, divergent boundaries, and transform boundaries. Let's explore how each of these types contributes to the formation of volcanoes. Convergent plate boundaries. Convergent boundaries occur when two plates collide or come together. There are two types of convergent boundaries: oceanic continental and oceanic oceanic. A. Oceanic continental convergence. When an oceanic plate collides with a continental plate, the denser oceanic plate is forced beneath the less dense continental plate in a process called subduction. As the oceanic plate sinks into the mantle, it begins to melt due to the increasing temperature and pressure. The molten rock, or magma, generated by the melting plate rises through the overlying continental crust, forming a volcanic arc on the continental side of the subduction zone. This results in the formation of explosive stratovolcanoes, characterized by their steep slopes and explosive eruptions. Examples of such volcanoes include Mount St. Helens in the United States and Mount Fuji in Japan. B. Oceanic-oceanic convergence. When two oceanic plates collide, one of them is typically subducted beneath the other due to density differences. As with oceanic continental convergence, the subducting plate melts and generates magma, which rises to the surface. This magma forms volcanic island arcs, such as the Aleutian Islands in Alaska and the Mariana Islands in the western Pacific Ocean. Divergent plate boundaries. Divergent boundaries occur when two plates move away from each other. This process creates a gap or rift between the plates. As the plates separate, magma from the mantle rises to fill the space, leading to the formation of new crust. The magma that reaches the surface forms volcanic activity, including volcanic eruptions and the creation of shield volcanoes. The Mid-Atlantic Ridge, located in the Atlantic Ocean, is an example of a divergent boundary with volcanic activity. Transform plate boundaries. Transform boundaries are characterized by plates sliding past each other horizontally. While they are not commonly associated with volcanic activity, some transform boundaries can exhibit localized volcanic activity due to the presence of fracture zones. The magma generation in these cases is not as well understood and can be attributed to complex geological processes. An example is the Garlock Fault in California, which has associated volcanic activity. It's important to note that plate boundaries are not always uniform, and variations in their characteristics can result in different types of volcanoes and volcanic activity. Additionally, hotspots, which are areas of intense heat within the mantle, can generate volcanic activity independently of plate boundaries. The interaction between plate tectonics and volcanic activity is a complex and ongoing area of scientific research. Lava domes are a type of volcano characterized by the formation of a steep-sided mound or dome-shaped structure composed of solidified lava. They are formed when highly viscous magma, which is thick and sticky, erupts onto the surface. The magma is typically rich in silica, which increases its viscosity. The formation of a lava dome often occurs during or after explosive volcanic eruptions. Here's a general overview of the process. Explosive eruption. Lava domes are often associated with explosive eruptions caused by the buildup of pressure within the magma chamber beneath the volcano. These eruptions can result in the ejection of volcanic ash, gases, and fragmented magma known as pyroclastic material. Viscous magma. Lava domes form when the magma erupted during the explosive phase is highly viscous. Viscosity refers to a material's resistance to flow. The high viscosity of the magma prevents it from flowing far from the vent. Instead, it piles up around the volcanic vent, forming a dome-shaped mound. Slow extrusion. The magma that forms a lava dome is often too thick to flow easily. Instead, it extrudes slowly from the vent, building up the dome over time. The extrusion can occur through cracks and fissures in the existing dome or by the squeezing out of magma from the central vent. Solidification. As the magma extrudes and piles up, it gradually cools and solidifies on the surface of the dome. The outer layers of the lava dome cool quickly, forming a solid crust, while the interior may remain partially molten. Continuing activity. Lava dome growth is typically a slow and continuous process. The dome may continue to grow as more magma is extruded, leading to the expansion of the existing dome or the formation of new lobes. However, dome growth can also be episodic, with periods of extrusion alternating with periods of relative quiescence. Lava domes can vary in size, ranging from a few meters to several kilometers in diameter. They are often associated with explosive eruptions, and their steep sides can make them prone to collapse and generate pyroclastic flows and hot ash avalanches. Some well-known examples of volcanoes with prominent lava domes include Mount St. Helens in the United States and Soufriere Hills in Montserrat. Understanding the behavior of lava domes and monitoring their activity is crucial for assessing volcanic hazards and protecting nearby populations. To get more informational videos like this, please subscribe our channel, share and press the bell icon. Thanks for watching.